How's that again? Presents. The truth about Mars. Although Mars is smaller than the Earth, 11% of Earth's mass, and 50% farther from the Sun than the Earth, its climate has important similarities, such as the presence of polar ice caps, seasonal changes and observable weather patterns. It has attracted sustained study from planetologists and climatologists. While Mars' climate has similarities to Earth's, including periodic ice ages, there are also important differences, such as much lower thermal inertia. Mars' atmosphere has a scale height of approximately 11 kilometers, 36,000 feet, 60% greater than that on Earth. The climate is of considerable relevance to the question of whether life is or ever has been present on the planet. Honoré Flaugergé's 1809 discovery of yellow clouds on the surface of Mars is the first known observation of Martian dust storms. Flaugergé also observed in 1813 significant polar ice waning during Martian springtime. His speculation that this meant that Mars was warmer than Earth proved inaccurate. Some scientists maintain that the great mass of the Tharsis volcanoes has had a major influence on Mars' climate. Erupting volcanoes give off great amounts of gas, mainly water vapor and CO2. Enough gas may have been released by volcanoes to have made the earlier Martian atmosphere thicker than Earth's. The volcanoes could also have emitted enough H2O to cover the whole Martian surface to a depth of 120 meters, 390 feet. Carbon dioxide is a greenhouse gas that raises a planet's temperature. It traps heat by absorbing infrared radiation. Thus, Tharsis volcanoes, by giving off CO2, could have made Mars more Earth-like in the past. Mars may have once had a much thicker and warmer atmosphere, and oceans or lakes may have been present. It has, however, proven extremely difficult to construct convincing global climate models for Mars which produce temperatures above 0 degrees Celsius, 32 degrees Fahrenheit, at any point in its history, although this may simply reflect problems in accurately calibrating such models. Mars' temperature and circulation vary every Martian year as expected for any planet with an atmosphere and axial tilt. Mars lacks oceans, a source of much interannual variation on Earth. Mars orbiter camera data beginning in March 1999 and covering 2.5 Martian years show that Martian weather tends to be more repeatable and hence more predictable than that of Earth. If an event occurs at a particular time of year in one year, the available data, sparse as it is, indicates that it is fairly likely to repeat the next year at nearly the same location, give or take a week. Martian dust storms can kick up fine particles in the atmosphere around which clouds can form. These clouds can form very high up to 100 kilometers, 62 miles, above the planet. The first images of Mars sent by Mariner 4 showed visible clouds in Mars' upper atmosphere. The clouds are very faint and can only be seen reflecting sunlight against the darkness of the night sky. In that respect, they look similar to mesospheric clouds, also known as noctilucent clouds, on Earth, which occur about 80 kilometers, 50 miles, above our planet. It has been suggested that Mars had a much thicker, warmer atmosphere early in its history. Much of this early atmosphere would have consisted of carbon dioxide. Such an atmosphere would have raised the temperature, at least in some places, to above the freezing point of water. With the higher temperature, running water could have carved out the many channels and outflow valleys that are common on the planet. It also may have gathered together to form lakes and maybe an ocean. Some researchers have suggested that the atmosphere of Mars may have been many times as thick as the Earth's. However, research published in September 2015 advanced the idea that perhaps the early Martian atmosphere was not as thick as previously thought. Currently, the atmosphere is very thin. For many years, it was assumed that as with the Earth, most of the early carbon dioxide was locked up in minerals, called carbonates. However, despite the use of many orbiting instruments that looked for carbonates, very few carbonate deposits have been found. To date, it is thought that much of the carbon dioxide in the Martian air was removed by the solar wind. Researchers have discovered a two-step process that sends the gas into space. Ultraviolet light from the sun could strike a carbon dioxide molecule, breaking it into carbon monoxide and oxygen. A second photon of ultraviolet light could subsequently break the carbon monoxide into oxygen and carbon, which would get enough energy to escape the planet. In this process, the light isotope of carbon, 12C, would be most likely to leave the atmosphere. Hence, the carbon dioxide left in the atmosphere would be enriched with the heavy isotope, 13C. This higher level of the heavy isotope is what was found by the Curiosity rover on Mars. The Martian atmosphere is composed mainly of carbon dioxide and has a mean surface pressure of about 600 pascals (Pa), much lower than the Earth's 101,000 Pa. One effect of this is that Mars' atmosphere can react much more quickly to a given energy input than Earth's atmosphere. As a consequence, Mars is subject to strong thermal tides produced by solar heating rather than a gravitational influence. These tides can be significant, being up to 10% of the total atmospheric pressure, typically about 50 Pa. Earth's atmosphere experiences similar diurnal and semidiurnal tides, but their effect is less noticeable because of Earth's much greater atmospheric mass. The surface of Mars has a very low thermal inertia, which means it heats quickly when the sun shines on it. Typical daily temperature swings away from the polar regions are around 100 Kelvin. On Earth, winds often develop in areas where thermal inertia changes suddenly, such as from sea to land. There are no seas on Mars, but there are areas where the thermal inertia of the soil changes, leading to morning and evening winds akin to the sea breezes on Earth. At low latitudes the Hadley circulation dominates, and is essentially the same as the process which on Earth generates the trade winds. At higher latitudes a series of high and low pressure areas, called baroclinic pressure waves, dominate the weather. Mars is drier and colder than Earth, and in consequence dust raised by these winds tends to remain in the atmosphere longer than on Earth, as there is no precipitation to wash it out, excepting CO2 snowfall. One of the major differences between Mars and Earth's Hadley circulations is their speed, which is measured on an overturning time scale. The overturning time scale on Mars is about 100 Martian days, while on Earth it is over a year. Katabatic winds, or drainage atmospheric flows, are winds that are created by cool dense air sinking and accelerating down sloping terrains through gravitational force, found most commonly on Earth, affecting the elevated ice sheets of Greenland and Antarctica. Katabatic winds can also be found affecting parts of Mars with intense clear-cut downslope circulations, such as Valles Marineris, Olympus Mons, and both the northern and southern polar cap. They can be identified by multiple different surface morphological features in the polar regions, such as dune fields and frost streaks. Due to the low thermal inertia of Mars, thin CO2 atmosphere and the short radiative time scales, katabatic winds on Mars are 2 to 3 times stronger than those on Earth and take place on large areas of land with weak ambient winds, sloping terrain, and near surface temperature inversions or radiative cooling of the surface and atmosphere. The low density of the Martian atmosphere means that winds of 18 to 22 miles per second, 65 to 79 kilometers per hour, are needed to lift dust from the surface. But since Mars is so dry, the dust can stay in the atmosphere far longer than on Earth, where it is soon washed out by rain. It is thought that Martian dust storms can lead to atmospheric electrical phenomena. Dust grains are known to become electrically charged upon colliding with the ground or with other grains. Theoretical, computational and experimental analyses of lab-scale dusty flows and full-scale dust devils on Earth indicate that self-induced electricity, including lightning, is a common phenomenon in turbulent flows laden with dust. On Mars, this tendency would be compounded by the low pressure of the atmosphere, which would translate into much lower electric fields required for breakdown. As a result, aerodynamic segregation of dust at both meso and macro scales could easily lead to a sufficiently large separation of charges to produce local electrical breakdown in dust clouds above the ground. The process of geological saltation is quite important on Mars as a mechanism for adding particulates to the atmosphere. Saltating sand particles have been observed on the Merspirit rover. Theory and real-world observations have not agreed with each other. Classical theory missing up to half of real-world saltating particles. A model more closely in accord with real-world observations suggests that saltating particles create an electrical field that increases the saltation effect. Mars grains saltate in 100 times higher and longer trajectories and reach 5 to 10 times higher velocities than Earth grains do. Mars has an axial tilt of 25.2 degrees. This means that there are seasons on Mars, just as on Earth. The eccentricity of Mars' orbit is 0.1, much greater than the Earth's present orbital eccentricity of about 0.02. The large eccentricity causes the insolation on Mars to vary as the planet orbits the Sun. The Martian year lasts 687 days, roughly 2 Earth years. As on Earth, Mars' obliquity dominates the seasons, but, because of the large eccentricity, winters in the southern hemisphere are long and cold while those in the north are short and relatively warm. It is now thought that ice accumulated when Mars' orbital tilt was very different from what it is now. The axis the planet spins on has considerable wobble, meaning its angle changes over time. A few million years ago, the tilt of the axis of Mars was 45 degrees instead of its present 25 degrees. Its tilt, also called obliquity, varies greatly because its two tiny moons cannot stabilize it like Earth's moon. Like Earth, the obliquity of Mars undergoes periodic changes which can lead to long-lasting changes in climate. Once again, the effect is more pronounced on Mars because it lacks the stabilizing influence of the large moon. As a result, the obliquity can alter by as much as 45 degrees. Jacques Loscar, of France's National Center for Scientific Research, argues that the effects of these periodic climate changes can be seen in the layered nature of the ice cap at the Martian North Pole. Current research suggests that Mars is in the warm interglacial period which has lasted more than 100,000 years. Though at its current state, even if microbial life manages to exist on Mars, it is still inhabitable to humans.